All right, so in this one, again, we're going to start with a surface integral, and we're going to switch it to a triple integral. So we're given this interesting looking vector field, and we're given our S is the surface of this region that's bounded by all this stuff. You should not look at my picture, I'll kind of highlight it out, and pause the video and try and sketch that region yourself just for practice, especially if you had any trouble with the triple integral setup. So I would really encourage you to do that just as a learning process. But anyway, I went ahead and had the picture sketched, and it's still not great, but it was definitely good to sketch it not live. And that's what I came up with. So you can see the different pieces. The cylinder, you're stretching this along the y-axis. I should put my y here and my x and my z. You're stretching the cylinder along the y-axis, and so it just goes forever like this, opening down. Z equals 0 is just the floor. That's the plane. Y equals 0 is the back here. And then y plus z equals 2. That's this plane that sort of slices this way. And it's, well, it needs to line up with my cut there, but it slices off and leaves us a face on this cylinder. And so please realize, again, like the last example, you could work this out as a surface integral, but you'd have to think about it as first this surface. That's not that bad of a surface, but still, first this surface. Then you'd have to think about it as the roof of this guy, which was going to be the size of this parabolic cylinder opening down. The boundary there is going to get kind of interesting. Then you'd have to work on this surface, the front, plus you'd have to work on the back surface. So it would take you parameterizing 4 different surfaces and then adding up what you got in each case. Well, again, not really my idea of fun, even though I enjoy doing mathematics. So we're going to try and make use of the divergence theorem, and the divergence theorem says, hey, if you're working out the surface integral of a closed surface and everything is nice enough, which in this case it is, then you can switch this to the triple integral over the solid E. I'm thinking of E as the solid here, whereas S is just the shell, the surface of this guy. Triple integral over the solid E of the divergence of F dV. And now we look up at our vector field F somewhat with fear and trembling, looking at all these nasty little formulas in here. But actually, I mean, it's not that bad. And the point is, you can, I/your book or whoever, can come up with some really sketchy looking vector fields whose divergence is actually not that bad. Look at this one with me. The divergence here, partial x of the first component, you just get a y. So we'll just, let's just work through it, maybe down here in purple. So we'll just compute this. The divergence of f is what? Y plus partial y of this guy, you just get a 2y. The other part falls out. And then partial z of this is just 0. So the divergence of f is just 3y, which really isn't too bad. So we're looking at the triple integral. I need to switch away from purple. The triple integral over the solid E of 3y dv. Let's go back to black. And so now I've just got to set this triple integral up. And again, if you need some practice with that, if you struggled with this in Chapter 12, why don't you pause the video and try and set it up yourself. Think about your first cut, which way you're going to cut it, and then think about those bounds. All right, so I'm looking at this, and I guess our typical approach would be to ask, can we cut it first along the z direction? And the answer is, well, you sort of get into trouble because you have 2 different roofs. You have the paraboloid here and then the plane. So that really wouldn't be the ideal way to cut it. If I cut it with respect to x first, then I'm bouncing off of the same surface. That's really not ideal. There are ways to deal with some of this, but the best way, I think, to start is to cut it with respect to y, because you go from 0 out to this plane, which you can solve for the equation. So that's how I'm going to do it. I'm going to write this as triple integral, and I'm going to go ahead and put my 3y, and then the order that I want, I'm going to start with y, and I'm going to get those bounds. So y is going from 0 to this equation. This equation was the plane, y plus z equals 2. Solve for y is 2 minus z. So y goes from 0 to the plane out front, 2 minus z. Now we stand here, and we look that way, and we're going to think about what am I going to see when I face that? What shadow am I going to see? And you're going to see exactly this. That's the projection. And so you can sort of see I've got it set up right here. The equation that we're looking at is z equals 1 minus x squared. Of course, we said stop it at z equals 0. That was on here. So we don't keep going down. We stop it right here. And so you have to choose how to set this one up. And I would probably go ahead and cut it dz dx, because z goes from 0 to this, and then x goes from minus 1 to 1. Again, you can just solve where this is 0 to get the minus 1 and the 1. So I'm going to do dy dz dx. Z goes from 0 to, I need to add a little more space here just so you can read all my bounds. So z goes from 0 to 1 minus x squared, and x goes from negative 1 to 1. Now, some of the videos I've been working out some of these examples, trying to give you lots of detail. This one I'm not going to. This is all relatively clean. There's just a polynomial. Everything is really not too bad. So I would encourage you to pause the video and work this one out yourself. And when you do that, you should come up with 184 over 35. So that's not only is that the triple integral of the divergence, that's also the flux. And so this actually brings up a point that I wanted to make. When we talked about triple integrals and we said, hey, when you take a triple integral of anything other than 1, it's no longer volume, it's actually hypervolume. It's in some sense four-dimensional volume. And how is that useful? Well, here's another way that four-dimensional volume is useful. When you take this triple integral of this particular function, it gives you flux. You're measuring the flow, if you will, of this fluid modeled by F through your surface S. So just another interesting application for triple integrals. So let's break this video here. In the next video, I'm going to make a remark, and then I'll do an interesting example with you, and then we're going to call it a